All right, so today we'll actually continue with the lexical analysis, especially we're going to talk about regular expressions. But last time we kind of start with the alphabets and strings, and today we'll finish the definition about strings, language, and problem. So once we define all these terms, we can start talking about different notations for expressing languages. And regular expression will be the first one, and then DFA, NFA, and then etc. Okay, that's something we'll get into. Let's do a very quick recap about what we said last time, very quickly. Okay, so last time, we finished the last bit about the introduction, which is to show you guys some details about the so-called object relational bridge. So that one is just one example compiler. So this will be a little bit more similar to what you're going to develop for your project. I'm not saying exactly the same, but similar along that path. So this one here is definitely not a conventional, let's say C to assembly compiler. So it's definitely something that's more interesting for you to see the different possibility of doing compilation. So you guys can maybe go onto the details if you want to. So it can definitely give you more inspiration for the project for later. And then we talk about scanner, lexical analysis. So we talk about either you might get all the tokens recognized, in which case you're going to pass this stage for the lexical analysis, or if there's at least one token that's now recognized, in which case you're going to report some scanning error. So that's something you will also see when you actually try to study the Antler 4 tutorial videos later, about halfway through of this course. And then we talk about this kind of roadmap about what we're going to do. So we're going to finish about the definition for alphabet, string, language, and problem today in the first half, or maybe first 1/3. And then we're going to go on to talk about regular expressions. I think that might be the main topic for today. If I can, I'll try to do a little bit of DFA, but we'll do the more formulation, kind of the stuff about NFA, non-determinism, and also conversion later. It may have to be next week. But anyway, we'll go one step at a time. I think, as I said earlier in the introductory lecture, I mean the first class. So in the lecture, we're going to focus more on the theoretical foundation for the compiler, which will be regular expressions, the regular languages, and context-free languages. So these are the two things we have to focus more for the lectures. But in the actual project, you'll get lots of hands-on experience by finding some good teammates, right? As I said, so please do try to reach out to maybe your classmate in person during the break, after the class, before the class, and think about who you may want to work with in the second half of the course. I think that'll be crucial as well. All right, so we talk about alphabets. Very quickly, alphabet will just be non-empty set, cannot be empty, of characters. Right? So you may have characters 0 and 1. That's very typical for binary notation, what can be for maybe English alphabets, right? So you can review. And it is important for you to see that this particular way to specify the alphabets, or we'll see more notation like this, is called set comprehension. Meaning that you don't explicitly numerate all the members in the set explicitly. You don't do that. Instead, you simply specify some expression over here and then some predicate, which may be evaluated to either true or false. So the set itself is going to include all the members where the expression is going to satisfy this particular predicate. You will see lots of examples as we go through the formulation, but we're going to see more today as well. And there's something you guys will have to also, I can include maybe some background slides for you, just in case you want to review a little bit about logical notation. For example, implication, also conjunction, disjunction, for all, and exist. So these are the things that I assume you guys I'm pretty sure have seen that before in 1019 or 1090. So whenever you want to specify the predicate notation here for set comprehension, you will need these logical operators, but you will see them as well in the slides. But I can include maybe some background for you to review. Maybe that'll be beneficial for your written test and maybe for your exam for later. I'll do that later. And then just more example about alphabets over here. So we'll talk about string. Let's say we're given the alphabets for all the keys you can type on the keyboard, right? So that's one possible way to do it. And also we got, when we talk about string, you were saying it will be a string over some alphabets. For example, you will say 01010. Each individual character in the string is a member of the alphabets you're talking about, right? It's a simple set membership you can define. And we have some special string, just epsilon, empty string. And we also use a vertical bar, like an absolute value for the length of the string. And the final discussion we had last time was about identities, right? So we started with the string concatenation, and we said its identity will be the epsilon empty string, right? You can take a look at how we can somehow also talk about identities for other operations over here, right? That's also something we can explain in detail last time. All right, guys, any question for last time? All right, if no, let's now move on to talk more about strings before we define language. Okay, let's now do one step at a time. Sorry, so I have a little bit running nose. Just bear with me. Okay, so let me just make sure. Okay, good. All right, let's now move on to today. So I'm going to talk about strings, but I'll get to this part here. It's also on your slides, but we can develop the notation from scratch. So strings part 2. Let's now define some notation. Let's say we got some alphabet sigma. Let's say binary alphabet, 0 or 1. And there's a notation there, we put a superscript k over here. So that means we're talking about a set of strings of certain length k. All right, so the notation goes like this. So we simply say sigma to the power of k is going to be the set of strings of length k from certain alphabet sigma. Let's see one example here. Let's say we have the sigma being 0, 1. Let's say we got here. Let's say sigma is simply 0 and 1, which we thought last time. What can be the smallest value for k? Well, since k here denotes the length, what will be the shortest length? 0, right? So you can say sigma to the length of 0. So now, be careful, right? Precision is important. If you simply say this is simply epsilon over here, it's not exactly right, because we said it's going to be the set of strings. It's going to be a set. There's only one single string in this set, which is epsilon. So the way to put it would be like this. So sigma to the power of 0 would be the set of strings of length 0 from this particular alphabet, 0, 1. Right? That's the first one. And then, let's now move on a little bit. If I say sigma to the power of 1, this will be the set of strings of length 1. Of length 1, it could be either a string 0 or it can be string 1. Now you can notice one thing here. 0, 1 and 0, 1. They look the same. I agree. The way you write it, the way you type it on your computer, they look the same. However, you got to be very cautious about what they really mean. Okay? This one here, if you look at that, for example, the 0 over here is an alphabet. Or you can think it's a symbol, just a single character. On the other hand, the 0 over here is basically a string of length 1, which happens to contain just the character 0. All right? So this one here is a string of length 1. They're not exactly the same thing. Yes?
This would be the case for every alphabet, right? That the alphabet and the set of all...
Yes, exactly. Yeah, even if you say you got an English alphabet, in which case the sigma to the power of 1 will be A, comma, B, comma, C, right? Similar. It's exactly, yeah. Just for simplicity, we just use the binary alphabet for now. Okay, very good. And guys, how about this? Let's now try to work out something systematically, and then we can look at this one here, look at a more formal definition. What about sigma 2? However, before I do that, it's going to be something here, right? I'm going to put in. Before that, can we just ask you this? What's the cardinality of sigma 2? How many members are there in sigma to the power of 2? 4, right? Easy. Okay. So this, I'm pretty sure you know the general formula because we know for each length, so let's say it's here, we got 0, 0, 0, 1, 1, 0, 1, 1. Just for those of you who might be wondering, you basically got 2 positions to really choose. Each one of them, you got either 0 or 1. So 2 to the power of 2, basically, right? That's a simple math. I'm pretty sure you know. Okay, so that's about this, just an example, right? Let's now generalize it. So the one you see on the slides goes like this. Sigma to the power of k, and k can be 0, 1, 2, 3, 4, etc. So this is what we got. Let me copy that down on the page, and then we'll work out some precise definition. I think that'll be some nice exercise to review the logical operators. So sigma to the power of k will be the set of words or set of strings. W is like a string. And then over here, we say W is a string over sigma, the alphabets, and also the length of the string. So let me move this one a little bit here, and move one here. Okay, that'll be good for later. And then the length of W is exactly equal to K. Right? As you can see, the K here corresponds to the K over here. Right? However, we want to be as formal as we can. How can we make this part here more formal? Right? So here, W is basically a sequence of characters. But somehow we want to say in that kind of sequence of character, actually is really indeed a string over a sigma. Right? For example, if you look at this particular string, the W here, right? Let's say in the case of 2, right? 0, 0. How do we kind of express that 0, 0 indeed is a string over sigma, right? That's really something we want to work out very quickly. So the idea would be we want to somehow break down each string into individual characters. I want to say that each character is a member of the alphabets that we're talking about. Okay, let's now write it down. So this part here, we can make it more formal. We can say we assume that W is of the form character 0, character 1, character 2, all the way to character k minus 1. Right? You can see we start with 0, so it should be end with a k minus 1. So the length will be k. Right? We assume that every string is of this particular form. And then we want to make sure every character that contributes to the string is a member of the alphabets. Right? And now this is the part that we can review a little bit about universal quantification. Somehow we want to say every character over here is a member of the sigma, so that it will be a string over sigma, right? Now we're going to say for all. So how do we say for all is going to be universal quantification, but over what? In this case, we can say over all the range of indices for the character, 0, 1, 2, all the way to k minus 1. Okay? So what we can say here is, there are different ways to express it, but I'll just give you one way. You can say for every, let's say index I, such that what will be the range of I? It's going to be from 0 all the way to k minus 1. You can say 0 less than or equal to I less than or equal to k minus 1. Okay? And then you can say it is the case each one of them, C0, C1, C2, all the way to Ck minus 1, each one of them is a member of the alphabets. So here you can say C of I is a member of the alphabets, right here. So you can think about the I here is a dummy variable, which can be 0, can be 1, all the way to k minus 1. So we're saying each character here is a member of sigma. Okay, we'll just make it more formal. Yes?
The dot represents such that?
Oh, you mean the vertical bar and dot, right? Good. Let me say that very quickly. For quantification, So logical quantification. Just quick reminder. So you may have for every I such that you have some range. And then you have some property. I'll write it down first and I'll explain. And then some P of I. Also, you got existential quantification, I. And then you got some range. And also, you have some property. All right, so let's talk about it. I think that's worth the time. So think about the R over here is so-called the range of the quantification. It's going to define some universe of disclosure about what range of values you're going to quantify over. So this will be the range of dummy variables. Sometimes could be multiple variables to consider. Range, first of all. And also, this part here is about a property that should be satisfied. This one here will be the property. So this part here will be the property. However, for all and exist, the dot over there means slightly different things. Okay, but just before that. The vertical bar over here is such that. That means the same thing, just about range. This part here simply means such that. Okay, but let's talk about a dot for different. So this one, it is the case. For all over here, we only worry about those values of I which will satisfy the range. If they don't satisfy the range, we don't care. Okay? And for existential quantification, we want to somehow say there exists the I here such that this is satisfied and this is satisfied. So the meaning is not exactly the same. I'll give you more example, but just in a moment. Okay, let me just finish the definition here. So this will be just and. So here, when I talk about it is the case and also and. So this is when I actually got the this kind of syntax. I got the vertical bar, I got a bullet, vertical bar and bullet. But there's another way people also like to write. You can write either way for your test. Alternative for all. You can actually say for every I, and you simply put a dot over here. And then you're going to have the range of I implies the property of I. Also, we got the alternative to exist. And you got the range of I and the property of I. Okay, so you can see the difference over here. You actually got implication versus conjunction. Okay, let me just repeat the point. For the universal quantification, we're saying that if the range is actually satisfied, then we got to make sure the property is also satisfied. If the range is not satisfied, then we don't care. If you think about implication, well, again, it's logic, right? If you just recall the meaning for implication, we know that if the range is already false, then it doesn't really matter what the consequence is, right? It will just be true. Are these important? I would say yes, because later on we're going to use these kind of basic logical basics to define, to formulate DFA, NFA, and etc. So what I would do is maybe either before Thursday's class or before next Tuesday's class, I'm going to put up some background slides just for you guys. You can review. I think those are pretty complete for this purpose over here. In the programming test, you don't need to worry about such logical stuff. You don't have to. But for the written test and the exam, you may have to worry. Okay? But you have time to catch up, right? Okay, and then for this one here, since you got a conjunction here, that means you must have both the range and the property both satisfied. Because you know that in order for a conjunction to be true, both must be true. Okay. All right, having known this, let's go back to the example there and let's now write in a slightly different notation, right? So now you can see that this guy here, we use the such that, and also it is the case. But we can use another notation, okay? What we can do is we can say something equivalent. For every I, 0 less than equal to I less than or equal to k minus 1 implies Ci a member of sigma. Okay, so that's just another way. Yep. In the test, you can either write in this syntax here or you can write in this syntax here. But I think this one might give you a little bit more clarity because that one tells you exactly what the quantification really mean in the case of for all and versus conjunction for the exist. Yeah?
Sorry, can you say what the alternative is and what dots is it still it's the case?
Oh, you mean this dot over here, right? Yeah. It is the case, yes. Yeah, you can think about, yeah, I see what you mean. So this one here, let me just point it out. So this one here and this one here, for both of them, it will be just the case. It is the case. But after that, it is either implication or conjunction. Okay, yeah. Okay, good. Well, we'll write into a little bit more about this later, and then we can explain more. All right, so that's about the formal definition for what it means for this notation here, right? Right here. Okay, that's the first one. Let's look at the second one. Right, that's something we just look at, and then sigma to the power of 0 is just empty string. But don't forget, it should be enclosed within a set. All right, what about sigma plus? That one there, nothing tricky. It simply say all the strings that has more than 0 length. Well, not empty string, basically. Okay. So that one there, the notation will be sigma plus. That one there is going to be either sigma 1, which is a set, union with sigma 2, which is a set, union with sigma 3, union all the way to potentially infinity, like an infinitely long string. Okay? And for this one here, you can actually use a set comprehension notation to specify that. Okay? This one here is going to be all the words W. And then we can say, first of all, W is a string over the alphabet of certain length. Okay? Of course, you can think about the way we define this one here is based on this notation here. Right? That's something we're just kind of building on top. Okay? And then we say that the K here must be strictly larger than 0. We don't include the possibility of 0. Okay? So it is important to notice that. Okay, so K here and the K here. Okay, sigma plus. Okay, the final definition to look at will be sigma star. Okay. Sigma star, basically just to say we want to include the possibility of an empty string. Okay. So here we can say sigma star over here. And then you can simply say it's going to be just sigma plus, which we define right here, where the length is strictly larger than 0. But now we do want to include the possibility of empty string. So that's why I put it here. Okay, so whenever you see the star over here, that means we do allow the possibility of empty string. Okay, so we talk about sigma to the power of k plus and star. So these for these notations, just make sure you kind of get used to them again. All right, any questions on on this?
Yes.
Yes, go ahead.
In the set of strings of length k, you put an and between the set enumeration and comprehension.
Mm-hmm.
But in the set of non-empty strings, you put an equal sign between the enumeration and the comprehension. It just means really the same thing.
Okay, let me just be Hutch. Okay, the first one you talk about, is it this one here?
So set of strings of length k.
Okay, this one here, sure.
And then in green, character 0 all the way to character k minus 1.
Mm-hmm.
And then there's an and in between. Or
Yes.
expression.
Mm-hmm.
But in the set of non-empty strings,
Okay.
sigma plus, there's an equal sign between the,
You mean here?
yeah.
Okay, let's see this. We're trying to define this one here, and this one here. Each one of them is simply a set of strings. We want to define what these sets are. For this one here, we use a single set comprehension notation right here,
Oh, I see.
right? And then we say that after the vertical bar, after vertical bar, it will be the green part and this one here, because we're just trying to make this part here more formal.
Okay.
Okay? On the other hand, for this one here, we say that, of course, this one can be defined by set comprehension. But we say at the same time, you can also understand it as it's just a union of all the positive length strings. And this one here, we just simply say, since we have already defined sigma plus, so we say it's going to be sigma plus with one more possibility, which is epsilon. In this case, we don't really need set comprehension, but if you want, we can also do that. Let me just do that for completeness. I can also say it's going to be all the string W, and W is sigma k, but now in this case, k will be larger than or equal to 0. Right? You can see the contrast over here. Larger than versus larger than equal to 0, right? We just include that possibility. Okay? Yeah, sometimes it might just be more than one way to express things mathematically. All right? All right, the next one, let's now look at some exercises. Okay, so I can definitely give you guys maybe some high-level hints. You can also take a look on your own as well. Okay, so let's say the first one. So for this question here, I'm not really asking you to enumerate all the strings of length 5 over the alphabets of A to Z, which we know got 26 possibilities, right? I'm not really asking you to enumerate them all. What I'm asking is, how many are there? Any idea for this one here? So that's the first exercise which we can try very quickly together. So let me put down the question here first. So question 1. So the cardinality of basically A, B, and then all the way to Z. That's the alphabets, and then to the power of 5. Let's take a look right here. Okay? You can see over here, this part over here is about all the strings over this alphabets of length 5. And we are asking, what's the cardinality of this particular set? Give it a try.
26 to the exponent of 5.
Yeah, that one's pretty straightforward. Because think about, we got 5 here, so we got 1, 2, 3, 4, 5. And for each one of them, we can have either A or B all the way to Z. So for that one there, we can have basically 26, possibility 26, and also 26. So 26 times 5 times, so 26 to the power 5, right? That's pretty straightforward. Okay. And the next one there, let's try to say, rather than just asking about cardinality, are you able to enumerate all these strings systematically? Let's try something a little bit smaller. So the second exercise goes like this. Let's say we want you to enumerate. Let's say we got the alphabets, let's say A, B, C. Okay? That's the alphabets. And then we say we want to get a set of strings of length 4. Can you somehow systematically numerate the set of strings over here? But of course, we know that there are 3 to the power of 4 strings in this set. All right, so this is computed the same way as how we did it in the previous one. It's definitely a smaller number, but now the question is, can you numerate systematically? Okay, so here I just want to share with you some way to actually do it, right? So the way I'm going to do it is draw a little bit like a tree diagram. Okay, I want to show it to you. Okay, so think about, we start with the top. The first, well, it's going to be 4, right? The first character can either be A, B, or C. The first character can be A, B, or C. So it can be either A, or B, or C. And then the second character over here can either be A, or B, or C. And this one here, A, or B, or C. A, or B, or C. And this one here, A, or B, or C. Right? You can see, given that the first character is A, the second character again can be A, or B, or C. Given that the first character is B, the second character can also be A, or B, or C. You know, etc. You get an idea. I'll pause over here, but of course you can try to continue. It's not very big, so I think it's still doable on the paper. So let's say we got a very big tree. What then? Not very nicely, if you try to find out every tree-to-leaf path in the tree, you will be able to find a string. For example, you can see that A over here is part of the substring for one string, right? Or it could be maybe B and then C. That's also part of it. So you just want to find all the paths. So that'll be much easier for you to find the path systematically. Okay? And to really complete this, I'll leave it to you. I hope you get an idea. So this one is going to be A, etc. And this one here is going to be B, C, etc. Okay? And you should be able to find out all the 3 to the power 4 strings for that particular set. All right? All right, the third exercise. The second one and the third one. Somehow you want to explain the difference between sigma and sigma to the power of 1. Actually, that's something we already discussed, right, just earlier. Sigma here, just alphabets. But somehow sigma to the power of 1 will be the set of strings over that sigma of length 1. Right? So for the detailed comparison, you can also look at what I just discussed a few minutes ago. You can take a look at that. All right, so that one there, I'll leave it to you. You can definitely refer to it later. So I'll just make a note here. So for number 3 here, it's going to be sigma versus sigma to the power of 1. You're going to remember this is alphabets set. On the other hand, this one here is a set of strings. All right. One more exercise. This one here is to prove or disapprove. All right, let's take a look at this one here. I wouldn't really prove or disapprove here. I'll let you think about, but I'll give you a little bit hints. Okay, the direction. Number 4. So we want to prove or disapprove. We say that sigma 1 alphabets. Let's say we got another alphabets, sigma 2. So here we're saying that if somehow sigma 1 is less than or equal to the size of sigma 2. So here we only talk about alphabets. Somehow we know about the relationship between the alphabets. What about their corresponding strings? Right? We want to know how those two sets are related to each other. So here the claim is that implies sigma 1 star subset of sigma 2 star. Okay, so this part over here is not about the relationship between the alphabets anymore. It's about their corresponding strings, including length 0, length 1, length 2, all the way to length infinity, potentially. So this one here is about the relationship between their strings. Okay, this one here, you should be able to do it. Okay, you want to think about whether that's true or false, and then show it. All right, so that's about the strings now I want to cover, right? You got some that definition there. You also got some exercise over there. Hopefully that's enough to review. Okay. Next level. So we talk about alphabets. We talk about strings. Let's now talk about languages. That'll be the next level. Okay. Some definition first. Languages. So we say a language over some alphabets. And we assume the alphabet is actually finite, cannot be infinite for the alphabet. It's going to be a set of strings for the language. I'll give you some example pretty soon. And we say L is a subset of sigma star. Okay, let's now visualize this right away. Okay, so we talk about language. So by definition, we say that L, some language, is a subset of sigma star. So here, of course, we are saying that subset over here, we say L could be the same large, equally large as the sigma star, but typically it's not the case. But it's okay, we just include over here. How do we visualize that? If you think about this will be all the strings possible for sigma. So this will be sigma star. And we're saying that L here is just about a subset of that. Okay? They could be the same large or could be different. Okay? So in the case where they are different, in that case, when L is a proper subset of sigma star. And if you guys remember, recall maybe from 1019 that maybe you took in the first or second year. So when I say something is a proper subset, that means guaranteed the cardinality of that is strictly smaller, right? Well, again, let's do some quick review example. You can say that 1, 2 is a subset of, for example, 1, 2, and 3. Also, you can say that 1, 2, which is strictly smaller, is also a proper subset of 1, 2, 3. On the other hand, you cannot say, for example, 1, 2 is a proper subset of 1, 2. You cannot say that. Because this one here got to be strictly smaller. Right? Just a definition for proper subset. Okay? Okay, let me complete with this notion. So when L over here is strictly smaller than sigma star, what does that mean? There is at least one. Okay, at least one here is important. At least one string, let's say W, such that. So this string here should be part of sigma star, but it does not belong to the language. This is actually important. Okay, I'll give you a very concrete example in just one moment. Such that the W is actually in the sigma star, but W is not in the language. Okay, there's a very critical insight right here, and I'll give you one example right away. Let's say this. Let's say we got a sigma of the keyboard, right? I think one of your fellow students asked me to enumerate about the keyboard alphabet, right? Let's take that for example. So let's say we got a sigma here, the keyboard. Or ASCII characters from the keyboard. Let's start with this alphabet set here. And let's think about this. What about sigma key star? Sigma key and then star. Guys, what would this mean? When I say sigma key to the power star, how do you explain this set over here? Yeah?
Universal set minus the sigma key.
Say it again, sorry?
Universal set minus sigma key.
I want something that's in more layman's term. When I say sigma key star, what does that mean? Yeah, go ahead.
Using the alphabet of keys over any length.
Any length, yes, that I agree. Okay, however, I was expecting something even more layman. But I'll go with yours. That one there tells me that it's going to be sigma key 0 union sigma key also 1 union sigma key and also 2, right? Union 2 all the way, right? And of course, this part over here is the sigma key plus. But what I was expecting from you guys is really to explain in even more layman's term. How about this? It will be any sequence of characters you can type from your keyboard. You can type as many as you like, right? Or let's say you launch an Eclipse editor, you want to type something, right? All right, so that's something we can write down. And then I'll continue, okay? Let's say any text that can be typed from keyboard. All right, that's one thing. And then let's now introduce one language. Let me use the same one on your slides. Let's say we have the L, and let me use a subscript, Java. Okay, it has something to do with Java. Let's now define what this language is. It's going to be all the string called program. All the program, and it's a set comprehension notation. But we can be slightly informal in the actual condition, right? Because somehow it's kind of hard to formulate. First of all, we say the program is a string. It should be a member of the sigma key star. That means the program itself is any sequence of character. Now we're going to say more, because not necessarily everything you type on your keyboard is going to be a valid Java program. We need to introduce some extra constraint. So this is where things will become handy. So I'm really trying to kind of show to you the L here is really like the L here. And the sigma key here, star, is really the here, right? Somehow we want to kind of understand what this member might be. Okay? So I'm going to introduce one condition, which is critical. And the proc, different way you can say that in English. You can say it compiles in Eclipse or has no compilation error, right? I'll just say proc compiles in Eclipse. So this extra condition is actually very important, right? This extra condition. This extra condition makes sure the proper subset relation actually exists. Because not necessarily everything you simply type that is a sequence of typable from the keyboard is going to be a valid Java program right away. Right? So that's really the difference between L and sigma star. Okay? Okay. All right, any question about this? So from this page here, we're basically trying to appreciate when you talk about a language L and also sigma star. Typically, it should be a proper subset. But just for general definition, we can say we include the possibility of equality. But it shouldn't really happen. there's got to be some member over here that can distinguish what's really valid within the language. Anything that's not valid, they only belong to the strings themselves. Okay. Yeah, think about this kind of definition. I think that's useful. Maybe it is something that you wouldn't appreciate as much when you first encountered them in 2001, but now hopefully we put it in a different context. It'll be a little bit better for you. All right, there will be some exercises which I may not go over today. I'll show to you. There's one slide of the review exercises for languages, right? Let's see here. Okay, so this one here just about some practice about set comprehension. So you can try different languages, right? I got 1, 2, and just two languages. Think about these two languages. Of course, each one of them should be a set. How do you actually specify them as formal as possible using set comprehensions? Okay, I'll give you some example solution maybe a little bit later, but I'd like you to try. We can just go over, if you want me to go over your solution, drop by my office hour. We can talk about it. How about this one here? This one here we can discuss right away. Oh, question? Give me one moment. I'll write down the question here. Oh, maybe you want to answer that one, right? Or
I haven't had my hand up, just paying attention.
okay, no worries. Give me one moment. So the second exercise here is to explain the difference between this one here and this one here. By the way, both of them can be languages, just a bit extreme. Because both of them are like a set of strings. So both of them are languages. But what's the difference between these two? Anybody would like to try? It's simple ones. What about let's say this is L1. How do you describe L1? What kind of language is that? Does that language accept any string, though? Does it contain any member?
Yeah.
It does, right? Only one. Well, that's really the critical question you want to answer. You want to see what will be the valid member in order to be in that particular language. In this case, the only acceptable string will be empty string. Okay? The set of a, how about singleton set? I believe you have heard about this term before. Singleton set of an empty string. On the other hand, you can see that over here, empty set is still a language. But somehow this language here is hilarious. There's no string that can be included, just empty, which is also possible. We're just going for extreme cases. So that will be L2. Empty set of strings. And if you think about the cardinality, so cardinality of L1 would just be 1. And the cardinality of L2 would be 0. All right. Okay? And then, if you look at more exercises, you can try number 3. That's why it's also interesting. You can also see different notations over here. Okay? You can think about this one here. I think this one here, again, can help you review the definition we just talked about, and also maybe something about subset relationship, right?
Sorry, can you go back to
You okay?
what is it? What's the difference? Like, what does singleton set of empty string?
It's a set, right? That contains only a single member. That member is an empty string. But this one here has no member.
Okay,
Yeah. Okay. Very good. Now think about number 3. And number 4 is just a little bit more proof you guys can think about. And I also give you some hints right here. I think number 4, think a little bit more about it. I think this one here is a bit trickier than the ones we just look at in the string exercise, right? Think about number 4. And number 5, again, proof or disapprove. Okay. And also I gave you some hints. Yeah, think about these exercises. I think quite nicely, put what you're supposed to know to review. Try them out, and then if you want me to go over your answer, drop by. Okay, we'll talk about it. Okay. All right, I think just one more slide, just about we have done alphabets, we have done strings, we have done languages, and final one, which would be something called problems. Once we define this, we are done with all the different levels of artifacts. And then after that, we can take a short break. After break, we'll talk about regular expression. That'll be the plan. Okay. Okay, problems. Well, in some ways, it's quite easy. So given a language, okay, so let's say this. Let me write right over here. Let's go over the definition together. Okay, right here. So we are really talking about problems. The way to formulate what a computational problem is whether or not some string W is a member of the language. And we can use our previous example in just one moment. But you want to think about the W here is kind of implicit in the context. You can think about the W here is really a member of sigma star. And the language that we're talking about over here is also sharing the same alphabet. Otherwise, it doesn't make sense if you're trying to solve a problem where you got incompatible alphabets. So this one here is also L, which we know is a subset of sigma star. Let's visualize this very quickly. Okay, let's use our Java example. Okay, so let's say here we got. You know what? Let's here. First of all, let's now start with this set here. Sorry, let me use this one here. Let's say we got a very big set. This one will be sigma, the key star. Let's say this set here contains all the possible strings you can type from the keyboard, everything, including those Java programs that compile and also those Java programs that do not compile. And then there will be a strictly smaller set, which will be all the compilable Java program. That's about here. So this one here will be the language of Java. And as we learned earlier, let me remind you very quickly, this one over here is a program. How about text? That does not qualify as a compilable Java program. And then the W here is really something that's inside. So this is compilable Java program. So a problem here is really asking, given arbitrary W, is it really in the L? It's guaranteed to be in the sigma star, for sure. But we want to know whether or not it's really in the language that we're talking about, meaning that we're solving the problem of including this particular compilation. So you can think about this problem here. This is a compilation problem. More precisely, whether or not an arbitrary string W compiles as a, for example, as a Java program. Right? You can see just a single membership here really represents the problem, but you want to understand what exactly it really means. Okay? So compilation problem, which is exactly relevant to this course, right? Compilation problem. We want to know if any arbitrary string that's over a particular alphabet we're talking about, is it really a member in the language? Okay. All right, any question? Okay, awesome. Sure. You mean this one here? Okay. Whether or not an arbitrary string W compiles. And then, for example, whether or not it compiles as a Java program, or whether it compiles as a C++ program, right? Just compiles in general. So I'm just trying to use this one to say this can be a way to really formulate what a compilation problem is, which is important for this course, right? Of course, in your case, for the projects, you're somehow going to implement this membership right here in your projects. And what me and TA will do is try some arbitrary string on your compiler. You got to tell me whether or not it belongs to the language that we describe in the project description. Something like that. Good. All right. All right, guys, why don't we take a very short break, and then by taking attendance, and then we'll talk about regular expression right after the break. All right, so before the break, we're done with the alphabets, strings, and language and problems. And now we can move on to regular expression. So that'll be basically the first one we're going to talk about for defining pattern, really. Let's go over some basic, and then we're going to, again, since we're reviewing the foundation, so things will get a little bit formal. But I'll walk you through all the details. Let's look at some basic definition or introduction. So regular expression, they are language-defining notation. Specifically, we are defining regular languages as opposed to context-free languages. Especially when we are defining regular languages, they are not recursive in their nature. Once we get to the context-free languages, they will be somehow recursive, but not for this one here. Okay, so regular. And they are equally expressive as what we're going to talk about later. So after regular expression, we're going to talk about DFA, and also NFA, and also epsilon NFA. So these are the other three notations. So we're going to learn about 4 different notations for defining regular languages. However, it's really, you cannot claim like which one is more expressive because you can convert from one into another and vice versa. But we might say sometimes maybe for a particular pattern of the language, it might be a little bit easier or more user-friendly for you to specify using one but not the other. But you can always convert. Let's say, for example, if I ask you to define some language using DFA, it may not be so easy for you to do that right away. So what you may want to do is you may just want to specify the language maybe using epsilon NFA, first of all, with some non-determinism and epsilon transition. Once you have done the version in epsilon NFA, you can convert that into DFA. That will be the answer, right? Anyway, so just an idea. But we'll see that also later once we get to these notations later. Okay, but they are equally expressive. And it is important to know that regular expression is the only one that's actually textual. You got to write some text. So it's also easier for us to manipulate some formal definition, which we'll introduce some today. And for example, here, what exactly is this notation here? You don't need to answer it to me right now. I just want to give you some example, right? So this will be one example, regular expressions. And of course, we're going to learn about what exactly it means when we say, what exactly do we mean by having a star? And what does it really mean when we have a plus, right? We got different notation there. And also, what does it really mean when we got 0, 1, star putting together, right? That's something we got to define. Okay, so that will be the actual language, but we'll get there a little bit later. Okay, for now, just put it there. You can review that later. And also, this will be another regular expression, which seems a little bit more complicated. And what does that correspond to? It will be just another language over here. Okay, but it turns out this should be odd number of ones. I'm pretty sure this is more like a hello world example you did for DFA. Right? I'm pretty sure you can construct a DFA. But this one here, if you want to put it in regular expression, it might be not as straightforward. So that's what I really meant by there might be certain patterns, it will be easier to use a particular notation. But it doesn't really mean other notation that will make it a little bit harder to specify are not as expressive. It's not a way to claim it, right? So all the notation are equally expressive. All right, let's now regular expression, use more user-friendly sometimes, right? For a certain problem. And if you are into web programming, if you want to specify anything for textual search, it can actually use a regular expression, right? Let's say if you try to create a new account for Gmail, there's some regular expression checks behind the scene. Let's say if you try to come up with a new username that does not conform to the rules, maybe you would say, I want to start with a special symbol followed by some character. You wouldn't be allowed because you have to start with non-symbol for your username, things like that. Okay, regular expression, and then provably equivalent. We wouldn't really prove them, but we're going to show you that they are kind of equivalent to each other by doing some conversion. Specifically, later, we're going to spend quite a bit of time, hopefully not too long. We're going to see how exactly we can convert from NFA into DFA. That's something important. We're going to do it, okay? But not today. All right, just one slide about very quick of the introduction. And of course, auto notation, they are only defining regular languages, which is not recursive in their nature. Again, let me emphasize. All right, let's talk about some operations. So in the following pages, I'm going to give you some very explicit cues. We're going to first of all talk about how we can somehow define languages, and also what will be the different languages. As we learned before the break, a language is simply a set of strings. So if you want to think about how you can manipulate regular languages, you're basically just manipulating set operations. Okay, let's talk about that one first before we see some operators for a regular expression. Okay, let's do one thing at a time. Okay, let me just dive directly into here. And the first one here, regular language operation, right? Again, regular language here is simply just a language. It's going to be a set of strings. So this one is saying, if I got regular language L, regular language M, if I use a union operator, I can have a larger regular language, union. That one's pretty simple, right? But what will be the definition, right? So here we can practice a little bit more about set comprehension. It's just going to be a set where each member string W can either come from L or can come from M. So I can say W can either be from L or it can be from M. This one should not be surprising at all. That's just how you define a union operator, right? And example right away. Let's say we got L here, M here. L is simply A, B, B, C, C, A. Of course, we're assuming that the alphabet is A, B, C, of course, right? So now, here, let's see, L union M will be all the strings. A, B, B, C, C, A, B, A, C, B. That one there, very straightforward. Nothing else to say, right? Union. The second one there is slightly trickier about concatenation, right? Let's see the definition first. Informally, if I say, I want to say language L concatenated with language M. Language L concatenated with language M. I am going to get another language that is going to be larger. But however, that larger language there is not going to be like a union that's straightforward. Let's go over the definition. Definition tells you that because L appears first, we're going to choose some string from L and use that here. And choose some string here from M and use it here. And concatenate the two strings together. Okay? Conceptually, okay? Think about, we're going to choose some W from here. Let's say choose X. Choose some string X that's in L. And then we're going to choose another string from M. Let's call it Y. So we choose these two strings separately, but we're going to concatenate them to get X and Y. and we got all such concatenation x and y. We talked about string concatenation earlier. When we got all such concatenated string together, it's going to define a new language Ln. Okay, let's now put it down as formal definition. So it's going to be basically some expression which will be x concatenated with y. And let me note right away, this guy here is string concatenation. That is, when we are trying to define language concatenation, we have to use, let me say it again. Language concatenation boils down into string concatenation, which makes sense. You want to get down to the basic units. Okay? X and Y, such that, straightforward, X should be a member of L, and also Y should be a member of N. Okay? That's the formal definition, which doesn't seem to be too complicated, but let's just do a concrete example just to make sure you're okay. Let's use this example here. Okay? So now we got L concatenated with N, which would be, so the first part can either be AB, BC, or CA. And the second part can either be BA or CB. Okay? Let's say given that the first part is already AB. Oh, you know what? How about this? I'll make it even more explicit for you. Think about this part here is L. Think about this part here is M. Okay? So the first part here can be, for example, AB. Concatenated with, for example, it can be concatenated with BA. And then we also got AB and then CB. So given that the first part is AB, the second part can either be BA or it can be CB right here. Okay? Yeah, just in case, this one is CB. Okay, let's make it complete. Or it could be that we actually got the first part is BC and then BA. And also we got BC and then we got CB. And finally, the first part could be CA, right? So also we got CA, CA, BA. And finally, we actually got CA and also CB. That's the full set of members for language concatenation. Okay? And if you think about it, what will be the cardinality? Cardinality of L followed by M will be, because the first part over here is about the concatenation from, well, the first part here is about some string chosen from L. So it's going to be about how large L is. And the second part, like a Y here, is about choosing something from M. It depends on how large M is. And we talk about all the permutation. So multiply by. Right? Okay? Straightforward. Right? All right, let's now talk about the third possibility, or the third notation. We talk about union, we talk about concatenation, and the third one, let me remind you about the name, is called Kleene closure, or Kleene star. Let me look at the name. Let's look at the name first. Okay, so we are done with the union, concatenation. It's a Kleene closure or Kleene star. All right? By definition, it's going to be this. Okay? I'll get to the final definition here in just one moment. Okay? It goes like this. We talk about alphabets, right? If you remember what we said earlier, just recall. Before the break, we talk about sigma to the power 0, sigma to the power of 1, etc., right? I want you guys to recall exactly what it meant, right? Just remember. But now we're going to talk about exponents applied to not alphabets, but to language. Okay? To do that, let me now open a new page. Let's talk about it. Given some language. So given some language L. Let's now use some example here. Let's say L will be AB and BA. AB and BC, how about that? Alphabet is still ABC. Okay. Let's now talk about stuff here. First of all, we say L to the power of 0, L to the power of 1, L to the power of 2, and etc. I'll get to L to the power of 0 in just one moment. That was slightly trickier. Okay? But L to the power of 1 simply means somehow I'm going to have just a single string, just X, such that X is chosen from L. You can think about L is somehow concatenated just once. Okay? And L to the power of 2 is like L is concatenated to itself twice. It will be L followed by L. All right? So if you remember, we talked about how we can concatenate two languages, L and M. But it's just that L and M happen to be the same language, which is okay, but in general. So this will be basically x1, x2, such that x1 is in L and also x2 is in L. Let's go a little bit further. Now let's say this. In general, L to the power of I. Let's say I is some number, arbitrarily large. That simply means I'm going to concatenate this language L here to itself for I times. So think about this part over here tells me I times. And how do I define that formally? Okay, let's take a look, which is interesting, right? I'm going to start with the first string X, second string X, X1, X2, all the way to Xi. I got I strings to be concatenated together. Each one of them is simply a string chosen from the same language, right? And I can use for all right here, okay? So here I can say, right here, for every, by the way, since I already got I here, I cannot use I again. I got to choose a different dummy variable. Let's choose J, for example. You can say for every J, 1 less than or equal to J, less than or equal to I, right? I'm quantifying over I, 1 to I, basically. And then the notation we just learned about universal quantification, it will be implication. And then we say xj, because I'm using this dummy variable here. Okay, so I got J here and J here. And that one there is going to be chosen from the same language. Okay, so take all the example we're trying to do here is case studies, right? You kind of review the set comprehension, logical operator, etc. If you got any trouble understanding of each one of them, any of them, let me know. Okay, we're almost there, and then I'll define the cleaning star, and then we're done for today. Just bear with me, 1 more minute or 2. Okay, so we got basically L, how about L0? L0 simply means we try to concatenate L to itself 0 times. If there's no concatenation, we get a string that's empty, basically. Okay? So think about this one here, that's kind of trickier, like a boundary case. Concatenate L to itself 0 times. And this one here, by definition, is going to be, by the way, it is not empty set because we are trying to concatenate 0 times. We still got some string over there. So that one there is just going to be epsilon. Okay? So this is like a boundary case you want to think a little bit more about. Okay, right here. Okay, let me just define the cleaning star and then we are done for today. Okay, we'll do more exercises, more clarification on Thursday. So give me one moment. Okay, let's go back here. What exactly is a cleaning star? Right? Let me reveal that right here. This one here is more like a generalized union. Okay, generalized union notation. This one here simply tells me the following: it's going to be a series of union of different languages. It's going to be I here is going to be anything larger than equal to 0, starting from 0, basically. L to the power of 0 union with L to the power of 1 union with L to the power of 2 union. Well, think about L star is about all the possible concatenation of L to itself for as many times as you like, including 0 time. Let's write this down. Okay. All possible concatenation of L to itself. All right, I think you guys got enough definition from today, so please review them before Thursday, and then Thursday we're going to build on top of this and talk more about regular expression. Thank you so much.